So where I left off last time is sort of introducing the issues and associated with electric power distribution. And what I want to do this time is flesh that out more carefully. And in the process, basically tell you a couple of different connected stories about electric power distribution and hopefully give you some useful insights into how electric power distribution works, because you live with it your whole life. I mean, you're going to be plugging things into wall sockets in all likelihood forever. I mean, unless you move to northern Canada or something and live off the land. Electricity is part of life. So where to start the stories? I'm going to start with the problem, addressing the problem that prompts the complexity of our electric power distribution system, and to show it to you. I've talked about it before, but let me actually show it to you. So when the electric light bulb had been properly invented, Edison and his team weren't the first people to play around with electric light bulbs. They get all the credit, but really it was about getting one that lasted more than a brief period. There were plenty of light bulbs around, they just didn't live long. So he managed to get one that was decently long-lived. And the way they work is they're just a simple electric circuit. Back in that era, they were using batteries for the most part. And the battery, along with a couple wires and a light bulb, was the whole story. When you connect up a battery and a light bulb in a circuit, and I hope you're all comfortable now with what the idea of a circuit is. You know, it's a racetrack for electric charge. Then the electric charge leaves the battery from its high voltage terminal, which is covered with positive charge. And so therefore, it's a great source of positive charge. The positive charges leave that battery through the first wire. They go to the light bulb filament. They go through the filament. They come back through the second wire and return to the low voltage terminal of the battery. And the battery then does work on them and sends them around the trip the second time. And again, what's happening is the battery is using its chemical potential energy to move around charged objects. In this case, little ions, little atomic pieces, fragments and assemblies, and moving around in such a way that it accumulates, for chemical reasons, extra positive charge on its positive terminal, extra negative charge on its negative terminal. They're moved there chemically, and they would love to get back together, and so they get back together by having the positive charge run its way through the circuit and go over where the negative charge is. I have mentioned, I'll just mention it again in case you're uncomfortable with it, secretly, the positive charge I'm describing going through the wires, it's really a fiction. What's really going through the wires is electrons going the other direction. And it's very hard to distinguish whether you've got positive charges going to your right or negative charges going to your left. You need sophisticated modern equipment basically to discover the difference. So the fiction is almost perfect. We'll see where it might run into trouble down the road. But the fact that I'm not talking about how electrons are flowing through the circuit is necessary, because otherwise we'll go crazy watching negative charge move its way around through things. It's just a nuisance. It's like watching negative money go through an economic system. It's just a nuisance. Debt. Okay, so we know that in order for this circuit to operate, the battery has to be providing electric power to the moving charge, and it is. It's providing 12 joules to every coulomb of charge that goes through it, which is to say it takes charge in at 0 volts and sends it out at 12 volts, having added 12 joules of energy per coulomb charge. That energy then is used the whole way through the circuit, including through the wires. So the wire is not a completely passive part of the circuit. It's charging a small fee, energy fee, for carrying the electric current. It's small because it's a decent wire. It's not very long. And so the electrical resistance of this wire is very, very small, and so we can almost pretend it's not important. The light bulb filament is a high resistance, meaning you have to push hard to get charge to go through it, and so it consumes a lot of the charge's electric power, the stored energy in the charge, to get the charge to go through at any decent rate, any decent current. So that's the story for a simple circuit like this, and people were lighting their houses this way. They would have batteries in the basement, and they would have light bulbs in the house. This is, great. The problem was the batteries run out of electric power periodically. You got to replace, do something to replace them. Big nuisance. So what happened was people started making electric, infrastructure where the electric power was provided. Thanks. The electric power was provided not on site. It came to you over wires. Wasn't that great? Well, there's a challenge associated with sending it over wires. So I had this battery glowing away. I can leave it glowing. It's a little dazzling, but that's life. So suppose we want to get we want to provide power from our batteries, which we've got at the warehouse, and we want to light that light bulb on the right side of the desk. Well, to do that, and of course I want to be a little careful here, wiring it up, well, I'm not in control of the far end because I don't want the two ends to touch and create a short circuit, create a circuit with no power consumer. So here are the other ends of those wires. So the battery's over there. There are two wires, one that connects to the negative terminal battery, one that connects to the positive terminal battery. And now I'm going to wire up, build a second circuit with this light bulb. Well, it works. The light bulb's lit. Electric charge is leaving the red positive terminal. Again, red is just the convention, widely used convention for the most positive voltage around. Black is the convention usually for the lowest voltage around. So charge is leaving the positive 12-volt terminal of the battery, coming through the wires, going through the light bulb, going back and through a second wire, and arriving at the negative terminal battery, the 0-volt terminal battery. But the bulb, it's the same bulb. These are indistinguishable bulbs. This one's pretty dim. What's the problem? And the problem is that wire now, which is quite long, and in this case we chose it deliberately to be a relatively thin, it's more like speaker wire than it is electric power carrying wire. It's got a high electrical resistance now because of its length and because of its thinness. It charges a big fee to carry electric current, and so while the voltage at the positive terminal of the battery is 12 volts, the voltage here at the corresponding end of the other end of that positive wire, it's not 12 volts anymore. It might be only 8 volts. And so the current that's traveling through here doesn't have as much energy per charge. And in order for it goes through the light bulb, and in order for it to get back, again, through a second wire, which has a significant electrical resistance, that wire is going to consume some of its power. It needs some voltage left, some energy per charge. So it not only does the charge arrive at only 8 volts probably, it has to leave at 4 volts to have enough energy to get left to flow through the wire at the rate it's flowing. So there's only really sort of like 4 volts left available to the light bulb itself. It now has a 4-volt voltage drop, which means it doesn't carry very much current because it doesn't you got to push hard on the current to get it through here. So it doesn't carry nearly as much current as it's supposed to, probably down by about a factor of 3, and that current, as it goes through, drops off less energy per unit of charge. So it's a double whammy. It's not getting enough energy, enough power, energy per time to light up properly. We're stuck. And this was the problem that Edison faced when he started trying to deliver electric power with, this is the origin of General Electric. It was Edison, anyway, I've lost track in my mind of the companies, how they evolved, whatever, but his illuminating company was having trouble delivering electric power and keeping the energy in that passing current. So the simple-minded solution is to go to thicker wires. So get rid of these thin, skinny guys, which are just they're big power hogs, and shift over. So take those guys out and shift over to big, fat wires. So these are much heavier duty. And here now I do have to be careful not to touch the pieces together. A circuit involving a car battery where there's all good conductors and no consumers of electric power, they're dangerous. For example, you drop a screwdriver across those two terminals of a car battery, the only thing limiting the flow of current now is the battery, really. And the battery will happily deliver 500 or 1,000 amperes of current. It will blow up a screwdriver. So there are lots of people who have batteries with chunks blown out of them or screwdrivers blown out of them by dropping them onto a car battery. Okay, so I'm now making a proper circuit that has a consumer of electric power, namely the light bulb, and now it's bright. And it's bright for the simple reason that these heavy wires don't charge as big an energy fee to carry the current they're supposed to. This is, again, is a current of about, I calculated 7 amperes the other day. So it's about a 7 ampere current goes through these wires even with a voltage drop of a fraction of a volt. So you don't need to push very hard to go through the fat copper wires. And so this was the approach Edison was taking, fat wires. Additionally, trying to put power sources strategically all throughout, like New York City, so that you were never very far from one. And it's doable, but it's very expensive because the current carrying at that time was copper. You have to use a good electrical conductor. Steel won't do it. Steel is a lousy conductor, not as bad as stainless, but it's stainless steel, but it's not good. And so you use copper, and it's expensive. So this was one approach. Along came Tesla and Westinghouse with a different approach using alternating current. So before I show you alternating current in action in this same system, let me remind you how a transformer works. And before I do that, let me just show you. I presented a graph not a graph, but a slide the other day that just was showing you the relationships between electricity and magnetism. Let me just revisit it and finish it. And it turns out that in our universe there are both electric and magnetic fields. When I first introduced them, they're not just a convenience or an inconvenience or a fiction. They're real. They exist in our universe for real. As we'll see shortly when I go into radio, you can have electric and magnetic fields with nothing else around, just those two. So they can exist on their own. Spoiler alert, radio waves and light both consist only of electric and magnetic fields. Okay, so magnetic fields are real, electric fields are real. How do you make them? A magnetic field, initially, we made them by just basically finding them in nature in the form of magnetic poles and subatomic particles. Basically, you find existing permanent magnets around. Great, you've got one of the iron oxides. Rust is non-magnetic, but another iron oxide, the black oxide of iron, is magnetic, and it formed natural occurring magnets in various places. So we had that around. That seemed to be the only source of magnetic fields. In electric fields, we certainly knew they were around because they live around electric charges. And subatomic particles carry electric charge, so there are electric fields around. It turns out that's an incomplete collection. Ultimately, magnetic fields can be produced not only by existing magnetic objects, but also whenever electric charges move, they produce a magnetic field. So electric currents are inherently magnetic. And this is an obscure one. It's necessary for the world of electricity and magnetism. It's necessary for radio waves and for light to work. It turns out that if you have an electric field and you change it with time, it's magnetic. It produces a magnetic field. How about producing electric fields? You can produce them first the old-fashioned way, which is just electric charges. And of course, subatomic particles often carry electric charges. But it turns out you can also make electric fields by moving magnetic poles or changing magnetic fields. So basically, as things change with time, magnetic fields produce electric fields, and electric fields produce magnetic fields. They become interrelated through variations in time. Okay? So that's this backdrop. Having done that, then let me turn this guy off, come back here, and revisit how a transformer works and try to make it as clear as I can. So here's a transformer. It has two coils, and we are going to move electric power, not immediately, but very shortly. we're going to move electric power from a circuit that involves the first coil, which we'll call the primary coil. It's just convention. People call the circuit that brings power to the transformer is typically called the primary coil. There's a second circuit here. It's a very strange circuit because it makes no connection with anything else. Why is this not coming apart? Please come apart. I'm doing something wrong. That's off. 1 second here, guys. Sticky. The second circuit's this circuit, connected to nothing. And it's a second coil of wire, which we'll call the secondary coil. And secondary coil is I don't know, it came apart. I got it. It was just, so it just confused me for a while. So the second coil, thanks, which we'll call the secondary coil, is where the power leaves the transformer. So power's going to come in, power's going to go out. For all practical purposes, power, like energy, is conserved in this transformer. I mean, power truly is conserved. It's just that a little bit of the power that comes in as electric power becomes thermal power, which is a waste. So we get like 95 or 98% of it's going to come out the other end. So that's the plan. And I want to make sure it's clear that we're going to go from one electric circuit, which is the circuit that involves this box and goes in effect to the electric company, and a second circuit which is connected to nothing. And power is going to move from the first circuit, the primary circuit, to the secondary circuit. But no charge will move between them. No magnetic pole will ultimately move between them. No, nothing. It's just going in effect through thin air. And it's facilitated by chunks of iron that magnetize nicely. But basically, there's no direct contact between these two circuits. So if I turn it on, it lights up. But let me not light it up first. Let me open the secondary circuit. So this secondary coil here, effectively nothing much is happening there. Not quite nothing, but not much. Well, so to start here, start here. It seems like I've connected a circuit. Now, I certainly have connected a circuit where the power company is providing electric power. It's giving us, and it's alternating current, which I have talked about a little about also, meaning that if I imagine the two wires that are going towards that coil, the wire that's white, the wire that's black, as they're going along, at different moments in time, the white wire has the higher voltage or the black wire has the higher voltage. They're going back and forth rhythmically, very fast, 60 full cycles per second. So this is a circuit. It's a circuit with the power company providing this wacky electric power where the voltages are bouncing up and down very fast. But there's often a voltage difference between one wire and the other, and therefore current would, of course, love to go from the high voltage to the low voltage, and it would light a light bulb if we were arranged that way. Well, the coil of wire is the only consumer of electric power in this circuit, and it's just wire. Well, if I took a paper clip and went from the one terminal to the other with a paper clip, there'd be a big spark. The paper clip would explode. This thing would probably blow its circuit in various other ways. Be a disaster, because we would have created once again essentially a short circuit, a circuit that had no consumer electric power in it. So somehow that coil of wire isn't doing that. It's not acting like a paper clip. What's it doing? Well, what it's doing is it is rhythmically building up a magnetic field and then unbuilding that magnetic field, and then building it up backwards and then unbuilding it up. The magnetic field, as the current is going back and forth like this, the current is flowing around the wire, initially, for example, no current, and then more and more and more one way until it reaches a peak, and then less and less and less until it reverses and then starts building up, and then reaches a peak and back. So this is a weird electromagnet that is magnetizing more and more one way and then more and more the other way. And I have to illustrate it with like gestures and stuff, otherwise I can't follow myself. So So it's alternately magnetizing one way and the other way. And that does a weird thing. That is a changing magnetic field. And changing magnetic fields, like claimed on the view graph, are electric. They produce electric fields. And those electric fields have a weird influence on the very current that creates them. The current that's going through this cable and that is operating this crazy alternating electromagnet, that current is being pushed backwards while it's building up the magnetic field and pushed forward as it's building down the magnetic field. In effect, this system fights the increase in current by pushing it backwards as it builds up. It fights the decrease in current subsequently by trying to keep the current going, by pushing it the way it's flowing as it tries to decrease. This whole notion is it's behaving as what's called an inductor. And I can show you an inductor in another context over here with the giant electromagnet. This guy, make sure I don't blow myself up. Or, there. Okay. When I turn this on, it's not magnetic now. When I turn it on, whoa, suddenly wildly magnetic, right? When I turn it off, not magnetic. There's a lot of interesting action going on here. When I first turn it on, does it instantly become incredibly strong magnet? No. It takes a fraction of a second for the current to get stronger and stronger, for this to become magnetic. As it's turning on, I won't close it yet. When I close that switch, this is initially not magnetic. The current begins to flow, and the current imagines, wow, free road. We can just flow like crazy. As it tries to do that, as it tries to go from no current to a whole lot of current, that change in magnetization of the whole structure means there's an increasing magnetic field. And changing magnetic fields are electric. The electric field that shows up as this magnet tries to turn on fights the turning on. It makes it hard for the magnet to turn on. So the rise in magnetization of the magnet is slowed by that effect. The very rising magnetization fights the rising magnetization. All the details, you can get lost in the math of this. This is, alas, some amount of life for third-year undergrad physics majors, right? Do those calculations. So the turning on process is delayed, waylaid by that effect, and it also, at the same time, something is happening, energy, because current is flowing in there, and current is indeed flowing from the high voltage to the low voltage. There's energy being released by the electric current. Where's it going? It's going into the magnetic field. It turns out, I told you magnets store energy by virtue of having a north pole and a south pole that have become separated, that it literally takes energy to magnetize a permanent magnet. It equivalently, or even more deeply, magnetic fields, the whole field that lives around a magnet contains energy. And that will be important in the near future when we look at radio waves and light and stuff. Radio waves and light carry energy. What form of energy? When you go out and bask in the sun, how's the energy coming to you from the sun? It's coming as light. How can light carry energy? It's carrying it in its electric and magnetic fields. Okay? So as this magnet is turning on, it's storing energy in the magnetic field. And it does that up to a point. Eventually it sort of settles down and becomes static and boring. And it just continues to consume electricity because it's not a perfect conductor, but that's life. Okay? The rising process, energy goes from electrical form to magnetic. How about when I open the switch? When I open the switch, what I'm asking to have happen is the current to go from large to zero. And the current tries to do that. But we've got all this energy stored in the magnetic field, and we're now reducing the current, which is electric. Reducing the magnetization. If you reduce the magnetization of those magnets, the magnetic field's shrinking. That creates an electric field. An electric field shows up, and what does it do? It tries to keep the current going. So during the turn-on process, the created what's called induced electric field tries to stop the current from rising. When you turn off the magnet, the reverse happens. An electric field shows up that tries to stop the current from decreasing. And that's why you see the big flaming arc there. I just turned on the current. It took about 1 second for the sounds to settle down over here. So it took about 1 second for that guy to magnetize, during which time the magnetic field was changing and these funny electric fields were in there. When I open it, watch the system try to keep the current going by way of a flaming arc. It's very hard to open that switch without making the arc because the electric fields push. Is it okay? So it's a complicated story, and I realize that it's hard to pass along with words. But that's what's happening in this when I turn on just the coil. Is the current first builds up a magnetic field, then it builds it down. Then it builds up the magnetic field the other way, because the alternating current is really going, it really does reverse. So energy is going into the magnetic field of this piece of iron, and then it's coming back out. Going in, coming back out. And where's the energy going when it comes back out? It actually goes back to the power company. So the energy actually is flowing into the magnet from the power company for 1/4 of a cycle. It then flows out for a 1/4 cycle, then it flows in upside down a 1/4 cycle, then it flows out another 1/4. It's sort of bouncing off this coil, not staying there. And that's why it doesn't burst into flames here. The energy is bouncing off that electromagnet. This is what's called a reactive load. The power company is aware of things like this around its power network because they can sense that somebody's storing the energy for a 1/4 cycle and then giving it back the next 1/4 cycle. It does affect the power company, and they have to compensate for it in various ways. But other than that, not a big deal. Okay? So far I hope I've explained to you why this coil of wire, as a consumer of electric power, doesn't burst into flames. It's not really a consumer of electric power. It's a storage device. It stores a little power and then gives it back. Stores it, gives it back. Stores it, gives it back. And under that guise, it's called an inductor. Name doesn't matter. Well, now I've got the second coil here. The second coil is living in the same environment magnetically and electrically as the first coil. And so as the energy is bouncing in and out of this first coil and the magnetic structure, the second coil notices, oh, energy's coming in, going out, coming in, going out, and it's going back out to the power company. And while this is turned off, the second coil can't actually do anything about it, except that the voltages at the two ends of the coil are doing weird things. The voltages actually are going up and down. Nobody's taking advantage of that, but that's the way things are. If I turn on, so that's the situation right now. The first coil is playing fun and games with electric power from the power companies. Take it in, send it out. The second coil is watching that happen. And when I turn on the second circuit, now some of the energy, instead of bouncing back to the electric company, comes out the other coil and doesn't go back to the electric company. The full details of why it doesn't go back to the electric company and how energy then moves from one to the other, I have them in the book, and ultimately they're very elegant, and physicists don't know them very well. I didn't know them very well until maybe 5 or 7 years ago. It turns out that these two coils are talking to each other in a very sophisticated way by way of their currents. If this one is drawing current, right now, the second coil has no current in it. So it has no magnetic field associated with that current. And because there's no magnetic field, there's no electric field produced by a non-existent current. Once I turn it on, the current that's now flowing in that secondary coil is important. It has its own magnetism. And because that current is changing with time, it has its own electric field. And that electric field talks back to the first coil and causes it to consume more electric power. So as you consume more power, electric power in the secondary circuit by turning on light bulbs, the primary circuit requests more electric power from the power company. It all works out self-consistently. So when I turn off the light, this transformer right now is just playing footsie with electric power. It's not actually consuming any. When I turn on the bulb, that changed. The primary circuit now is different. Some electric power that comes into the transformer never returns. Does not go back to the power company. It's conveyed to the secondary circuit and off it goes. Okay? That's detail. Any questions? You get out of question mode, but now life is life. All right. Come on. These guys do magnetize to some extent. So the ideal transformer, iron, magnetizes very easily and then demagnetizes very easily, so that you could magnetize it one way, then magnetize the other way, and back and forth, and it sort of has no memory. So you do not want hard magnetic materials in a transformer. They're not made out of the stuff that kitchen refrigerator magnets are made out of. They also want it to be reasonable price, so they make compromises, and this does not demagnetize perfectly. What I want to show you is this. This is a step-up transformer. I think I'll stick with this just to show you. The difference here is that this, I showed you on Friday, the energy is going to move from one circuit to the other. Again, we have an isolated secondary circuit. That's the secondary coil. It has many turns of wire, and therefore it experiences any electric fields around this chunk of iron many times, and much work can be done on charges that move with those electric fields. As a result, this circuit, although it doesn't actually have any closed piece, it's open circuit, the voltage gets so high at the two ends of the circuit that the charge, the electric field is so severe in that gap that it breaks down the air, which is to say it turns the air into a soup of charged fragments, also known as a plasma, which then is conducting. So this is now, whenever the spark is there, it's a complete circuit. It's just a weird complete circuit, and then it rises because of hot air rises. All right? So this is a step-up transformer. It is moving electric power from one circuit, the power company circuit, to a completely separate circuit over here. And it's trading voltage for current. This guy, because it has many turns in it, develops a huge rise in voltage, what's called an EMF. That's the traditional name for it. The increase in voltage between the low voltage and the high voltage ends becomes enormous, 11,000 volts. And that that's part of the story. The other part of the story is because the current flowing through that secondary circuit makes so many trips around the iron, it has a big magnetic influence, even if it's a small current. So a small current in that many turns of wire, they build on each other. The charges have many opportunities to add to the magnetic magnetization of the iron, and therefore you can't get very much current flowing through this wire before it produces big magnetic fields. Big changing magnetic fields has a big influence on the primary circuit. So if you draw these light bulbs could draw an ampere, 2 amperes, 3 amperes, something like that, through the circuit without really affecting the primary circuit very much. This thing, only 1,000th of an ampere, already starts to affect the current in the primary circuit. The reason I'm saying this is because energy really is conserved, and with it, power is conserved. Energy per time is conserved. So with this device, it provides 11,000 volt electric power, but very small currents of it, because the product of current times voltage is the power. If it's a voltage rise, it's the power being provided. If it's a voltage drop, it's the power being consumed. So these types of transformers, this being a step-up transformer, it provides higher voltages but less current, because the product of voltage times current has to be, it reflects the conservation of energy. Is that okay? Step-down transformers is the other way around. They provide very little voltage in an electric circuit, but lots of current can flow, because the product of the two tends to be small, so you get lots of current. Okay, the point of all this, let me go on to things that are of value. For the story, reminder, the reason the electric power is not distributed the way Edison had in mind is because as you put more and more people on the electrical wires, sharing the electric wires, and make those wires longer, and the electric wires themselves begin to consume too much electric power, and it becomes impractical and unacceptable. So with transformers, you can do something rather remarkable. With transformers, I mean, how to make sure I introduce this right. With so-called direct current, which is what a battery provides, where the current leaves the same wire, the same terminal of the battery all day, every day, nothing ever changes. It's just an electric activity. There are some magnetic fields around any current-carrying wire, but they're not changing with time, so they have no electric effect. So basically, any electromagnetic relationship that shows up in battery-powered electric circuits is kind of boring. Not much is happening. But if you switch over to electric current that is changing with time, so it becomes alternating current, now you have this interplay between electric and magnetic effects, and you can move power from one circuit to another. And the circuits can be different in important ways. So now, I had, just to remind you, let's go back to the old skinny wires, which seem completely useless for distributing electric power at a distance. I mean, this does not look promising. Those skinny wires look hopeless. What can we do to make the skinny wires usable? And here's what we do. We start with, not with a battery. So a battery provides direct current. We can't do anything useful with it in the way of interchanging power between circuits. Let's start with a source of electric power that is alternating. That has first one wire is high voltage, then the other wire, back and forth and back and forth. I'm going to start with that electric power at this point. I'm going to secretly get that alternating electric power from the power company, get it into the right shape, that it is basically the equivalent of 12-volt power. This light bulb, if I light it up using a battery, this light bulb lights like that. If I light it up instead using an alternating version of 12 volts, it lights up the same. I'm lighting, so pretend this isn't here. This is just my source of 12-volt alternating current, as though I could get it from a weird battery. Okay, so I could put a box around this and say magic. It looks the same. Light bulb can't tell the difference. And there's a little bit of a difference. The light bulb actually is having current flow through it one direction and then reverse and back and forth. And there are moments when there's no current flowing because it's a smooth sine. It follows trigonometric functions, sine. It goes back and forth. There is a moment, so the voltages are doing this, whoo, back and forth. And there is a moment of zero and so on. So that light has a little flicker to it because it really is getting a little brighter and dim. There's a lot of thermal inertia in effect in the filament. It doesn't heat up and cool down all that fast. And therefore, you don't notice that the current's going back and forth and back and forth. Furthermore, it doesn't care which way current goes through it. Like the filament is just a wire, just a lousy conductor wire. It doesn't care whether current goes left to right or right to left. Who cares? It's indifferent. So, point is, I've got now a source of weird power, 12 volt, and if I use that 12 volt directly to go light that light bulb up, it will light dimly also, because I'll be in the same situation. I will be trying to put too much current through the wires. But we can do better than that. And what we will do, and now let me wire this up in a way that's safe. I am going to step up the voltage for transmission and then step down the voltage for I never do remember how these guys wire. Let me try that. That should be okay. There you go. Okay. So I took my weird source of 12 volts, alternating current. I sent it into a step-up transformer. So it goes into this transformer through one circuit, and it comes out through a second circuit. This circuit is now all by itself. It's unrelated to the circuit that provided the power to begin with. And because I've got a step-down transformer here, it's unrelated with the current in this circuit also. There are 3 circuits on the table, basically, from my secret box over here, which is providing 12-volt AC power. That circuit coming through, involving these 2 wires, ends here. There's no electrical connection beyond that point. This is a new circuit. And the circuit goes through the wires, here are the skinny wires. It ends right here. And then the 3rd circuit begins. This circuit operates at 12 volts and a big current. This circuit also operates at 12 volts and a big current. But this circuit operates at maybe 120, or I don't know, it depends on how we wire this up, somewhere, well over 100 volts and much less current. So the current flowing in these wires now is reduced by maybe a factor of 10 or 20. As a result, the amount of push you need to get them to go through is reduced. The voltage drop in the wires is smaller because they're not carrying that much current. You don't have to push that hard. And so the wires aren't wasting as much electric power. Okay? So this is the whole scheme. Hopefully you can follow that. Let me turn this off. You can follow. This is how the electric power grid works. Is they create the electric power at whatever voltage and current is best for them to do that. Again, the current means how many charges are going by per second. The voltage is how much energy each of those charges is carrying. So they generate their power. They make it alternating, which turns out to be pretty natural for generating systems. The generating systems use moving magnets near coils of wire, or it turns out moving coils of wire near stationary magnets. That process, because it's cyclical, it tends to create alternating current as you go from one direction to the other, to one direction to the other, or one direction to the other. So the generators are all turning at a very, very carefully chosen speed, all together, all synchronous across, in fact, the entire United States. They're all rotating together because we're all connected by these power grid. So the current is sloshing one way or the other, back and forth. They then, for long-distance transmission, they send it to a second circuit, a circuit that involves much higher voltage. Let me get this picture up here. I gotta have something to talk with. So two transformers, 3 circuits. There's the generating circuit where they produce the alternating current. There's the transmission circuit, which is electrically insulated from the other circuits, but carries a smaller current of electric charges, each packed full of energy, and therefore at high voltage. So these cross-country circuits are, in effect, very high voltage circuits. They're kept safely away from people. They're up on the top of power poles and stuff like that. They go for many miles if necessary, but the current's so small that that's okay. They don't waste a lot of power. And then finally, when it's time to go into communities, you can't send like 200,000 volts into somebody's house. It's not going to work. They'll have lightning bolts. So they go through step-down transformers to convey the power to other circuits that are lower voltage. And was collecting pictures. Let's see. Here. This is a picture of some of the transformers at a substation. You've driven by these things or passed by these things, funny warehouses, open air places with all sorts of strange electrical equipment. These are transformers. These are the high voltage circuits on these super long insulators. These are the lower voltage. They're not low voltages, these guys. This is probably going from like 200, 300,000 volts down to a mere 50,000 volts for sending current around, electric power around a city. So they go from across the country to around a city. You make this step down. Other ones like this, let's see. You sometimes see things like this on a telephone pole, or more often you see this. Surely you've seen at least one of these guys. These are transformers. They're taking power from the high voltage circuits, which are up here, you see all by themselves, and they are moving the power to low voltage circuits that are in these big fat wires. Why the fat wires? Because the voltage is lower, the current's higher. Now they have to be more careful with the current. They have to use better electrical conductors for that. I had thought to talk about why 3. The 3 wires is called 3-phase. It's very common. It's very interesting, but I'll leave that. These are things you may see around your neighborhood, these green boxes. They're probably around the university too. I mean, if I didn't know they are. Oh, this is a photo I took this morning, actually, of birds on the wires. The wires, high voltage or low voltage, are always strategically separated, not just because they could have sparks if the voltage is too high and the electric field therefore gets too strong. But you don't want animals connecting one wire to another. They become flash bulbs. And birds, the wires are separated such that birds can perch on a single wire. They complete no circuit. And charge is going on them and off them and on them and off them as the voltage on the wire they happen to have chosen to stand on does its up and down. So it is a little weird for them. They can feel this a little bit. And those of you who came up here with the hair stand-up machine and put your hand on the ball, when there's a couple 100,000 volts on you can start to feel the crackles and stuff. So this is why birds are perfectly happy perching on these wires, which are probably 10,000 volt wires. They don't particularly like the really high tension wires. If you look at the cross-country circuits, it's too much voltage for them. They actually feel it. They feel that crackly stuff going on and off. They hate those wires, so they don't perch on them. People who repair those wires, which is fascinating, who go and service those wires, maintain them, they are often landed on the wires by helicopter. They ride the wires. They wear suits around them, electrically conducting suits, so all the charge is on the outside of the suit, not on them, to keep them comfortable. Otherwise, they don't like it. Okay, now that's good enough. Okay, last thing to talk about before I call it quits on electric power distribution. The outlets. They're around the room. Three pins in the outlet. What are those 3 pins? It turns out that only 2 of them are explicitly, deliberately involved in delivering electric power to you. The 2 slots. And the way they've got it arranged, standard electrical power distribution, the longer of the 2 slots, you've noticed that some electric plugs have a longer slot, two different length slots, and you can't plug the thing in the wrong way. The longer slot is what's called neutral. Its voltage is pretty nearly the voltage of the ground. It's supposed to be within 1 volt of the earth. The rounds opening truly is ground, and it should have the voltage of the earth. So 2 of those, basically 2 of the things you can connect to are within tiny voltage of 0. It's the last one, the short slot, that provides the electric power. It's alternately called load, hot, power. That wire does a weird thing. It goes up in voltage relative to the ground for a quarter cycle, then back down, and then it goes below the voltage of the outside and back up for a quarter. So it's going rising and falling, and it's actually rising and falling more than 120 volts. Why? Because the 120 volts that normal electric power nominally has is at an average-ish voltage. 120 volts AC should deliver the same power as 120 volts DC when it's delivering power to something like a light bulb or a toaster or a space heater or a hairdryer that don't care about the way electric power flows back and forth. So in order to get that average to work out right, the voltage of power has to rise above 120 volts because it spends a lot of time below 120 volts. So it goes above and comes back down. Then it goes below and below 100, minus 120 volts, and then it comes back. And it goes up and down. If you plotted it, it would be a sine wave or a cosine wave, it doesn't matter. Up and down and up and down. So for practical purposes, the one to be concerned about, the big slot and the round hole, you can touch those, don't do it. You can touch those all day. They should be, if wired correctly, they should be safe. It's the hot wire, or load power, the short slot that's dangerous. If you put your finger in there, you will probably get a little bit of a tingle because current will flow either out of it if it currently is at high voltage or into it if it's at low voltage, through you and through various things you're touching. You very easily create the other end of the circuit by touching something. Certainly if you touch a pipe or stand in a bucket of water, you're bad idea. So watch out for the narrow slot. There are devices called ground fault circuit interrupters, GFCI, which you've all interacted with also in bathrooms and on some of your things, your hairdryers, that watch for current going in or out of the hot wire and not coming back through the neutral wire. If there's an imbalance, they shut off the circuit. And when you press the test button, that's what you're doing. You're coaxing some current to leave that pairing. And then you press the reset button to get it back to work. Anyway, okay, I've said enough. We'll stop and pick it up on Wednesday.